Welcome back to the ANSYS 2D Meshing Masterclass. Linear or quadratic elements may look like a small setting in ANSYS, but this single choice can completely change your mesh quality, solution accuracy, and even solver stability. Before we begin, you'll find links to my other ANSYS tutorials, including ANSYS Fluent and related simulation topics, in the video description. If you're interested in one-on-one personalized training or project-based guidance, you can also contact me using the details provided there. In this session, our focus is element order in 2D meshing. We'll understand what linear and quadratic elements actually represent, how they behave during simulation, and finally, compare their mesh quality using a real ANSYS example. By the end of this video, you won't just know the difference, you'll know exactly which option to choose and why. Element order defines how displacement is calculated inside each finite element. This directly controls how accurately the solver captures bending behavior, curvature, and stress gradients. Two meshes may look almost identical on the screen, but if their element order is different, their results can be completely different. That's why element order is not just a meshing preference, it's a numerical accuracy decision. Let's start with linear elements. Linear elements have nodes only at the corners of the element. In 2D meshing, this means triangular elements with 3 nodes and quadrilateral elements with 4 nodes. Because the displacement varies linearly between these nodes, linear elements are computationally efficient and fast to solve. They work well for simple straight geometries, but they struggle to accurately represent bending and curved shapes. Now let's move to quadratic elements. Quadratic elements include additional mid-side nodes along each edge, allowing the displacement to vary in a curved manner instead of a straight line. In 2D, this results in triangular elements with 6 nodes and quadrilateral elements with 8 nodes. These extra nodes allow quadratic elements to follow curvature more naturally and capture bending and stress gradients much more accurately. To see this difference clearly, let's look at a real ANSYS example, a U-bend geometry. With linear elements, the minimum element quality is around 0.27, which is relatively poor for structural analysis. After switching to quadratic elements, without changing the mesh size, the minimum quality improves significantly to around 0.78. This happens because quadratic elements naturally follow curvature, while linear elements approximate the same shape using straight edges. So, even without refining the mesh, simply changing the element order can drastically improve mesh quality. To summarize, linear elements are fast and computationally efficient but limited in accuracy, especially for curved geometries. Quadratic elements are more computationally expensive, but they provide much better accuracy for bending, curvature, and stress prediction. A simple rule of thumb is this: if the geometry is straight and simple, linear elements may be sufficient. If the geometry is curved or accuracy matters, quadratic elements are usually the better choice. In the next part of this series, we'll move on to mesh methods and apply these concepts directly in ANSYS. We'll see how to switch element order, apply different mesh methods, and evaluate the results step by step. If you're finding this series helpful, don't forget to like the video, subscribe to the channel, and follow the complete ANSYS meshing tutorial series. Your support helps me create more in-depth engineering content like this.